Hello and welcome to Chapter 9, Section 3, Similar Right Triangles. The essential question is, how are altitudes and geometric means of right triangles related? What you will learn is how to identify similar right triangles and use the geometric means. The right triangle similarity theorem states that if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles that are formed are similar to the original triangle and to each other. All right, so what I mean by that is if I draw an altitude, or CD, here from our right angle to the hypotenuse, I'm going to create three triangles that are similar to each other. So we have our large triangle, which is here in red, A, B, C. Then we also have two other triangles that are formed. One small triangle here, say AD, C, and then we have another triangle that I'm going to trace in green here from D to C to B. Okay, so DCB. All right, so those are the three triangles that are similar to one another. Now here we are going to identify how to name these triangles, how to set them up so that we understand which angles correspond to each other. So what I'm going to do here first is I'm going to trace out our largest triangle, and then I'm going to pick a name for it. Now the name for this triangle the order of the vertices does not matter, as the following ones will definitely matter because they have to have corresponding parts. So what I'm going to do here, I'm just going to put the first one in alphabetical order as how I normally do it. So I would say RST, right? So triangle RST. Now I want us to take a moment to look at the order in which that I put the letters. So I'm gonna go ahead and make a list down here. So the first letter I chose was R, right? So what I'm gonna do here is I'm going to look at the type of angle that I chose. So I have R, which is kind of like an acute angle, S is an acute angle, and then T is our right angle. So I have to use some very descriptive things. So here, angle R looks like it was the smallest acute angle. All right, so let's keep that in mind, smallest acute. Next, let's say our second letter was angle S, okay, which is our largest acute angle. Okay, so hopefully that's not too confusing because large represents like a large angle, but it's just the largest of the acute angle. So we have two acute angles. We have a small one, we have a larger one. That's how I'm going to differentiate that. And then lastly, I'm going to do T, which is angle T. Angle T in the blue triangle that I traced is our right angle. Okay, so that's the order that we're going to follow to name the other two triangles in this similarity example. So next I'm going to go ahead and trace out this middle-sized triangle, which is created by our altitude UT. All right, and then I'm going to name it. Okay, this is why I made this list over here. So triangle RST is similar to triangle, and then I'm going to name it. Okay, so first thing I got to do is put the small acute angle from this red triangle. Which one of the angles, U, R, or T, is the smallest acute angle? Well, that's going to be R. So I'm going to also start with the letter R here because it is the small acute angle. Next, I'm going to put the largest acute angle, which would in this case be our angle T. And then finally, we're going to put our right angle, which we have as angle U. So that's how we name our right triangles. And then our last triangle is this very small one up here in the corner, SUT. Now, I want to go back a little bit and actually, let's just keep going. All right, so here we're going to name the triangle. All right, so we're going to start with the triangle symbol. Small acute. which one is the smallest of U, S, and T? Well, here I can tell that angle T is the smallest angle. The largest acute is going to be S. And then our right angle, again, is going to be angle U. Okay, now here's where I want to point out that although the first one I put in alphabetical order, and the second one also ended up in the alphabetical order, even though it's not really intentional, but our last one, boom, boom, T, S, and U, are all over the place. So the corresponding letters fall based on whatever you pick for your first triangle. Okay, other than that, everything else kind of aligns to the way the first order is set up, and by the order I mean this on the left side that I have. Okay, so all three of these triangles, the large blue one, the medium red one, and the small green one that I traced, are all similar to each other because of this right triangle altitude theorem. Okay, so let's use that to figure out if we can find the height of our triangle. So what I'm going to do here is I'm going to trace out this blue triangle on the outside, just like a rough sketch, trace around it, and then I'm going to sketch it on the side over here, just to kind of get the outline of it. It doesn't have to be 100% accurate, but it's just for labeling purposes and for us to see what the corresponding parts are. So let's do this labeling, and then I'm also going to label it with the pieces that are labeled with numbers. So 5.5 goes here, then 3.1, and then 6.3. All right, so we got that under control. So let's just go on to tracing our next triangle. So for this one, we want to get another piece of the similar triangle. So again, we have 3 in here. So we want to get a triangle that we can use to find our value h. So that could be either of the 2 triangles inside, but I'm going to go ahead and just use the small one. And I'm going to redraw it over here, just a smaller version of what I had drawn right up here. Okay, so it's just basically a smaller version. And this is just to kind of organize and see where everything goes. So now we label. Let's take a look at y. Y in the blue triangle was our right angle. So up here in this position of our small triangle, we need to also put our right angle, which would be W. Okay, next we have, let's go with Z. Z was in the small angle position, so I got to put the small angle, which in this case is Y, in the same place, same location that I put Z in. So I'm going to put my Y here. And lastly, we're going to take a look at, X. X was in the largest acute angle position, and in this case, X is also in the same position. And we know that this is accurate because X, according to the reflexive property, is a part of both triangles. So they should remain in the same position because they are congruent to each other. And similar triangles have congruent angles. Okay, next we're going to go ahead and label just like we did up at the top with the numbers and values that are corresponding. So between Y and X, it looks like I had a 3.1. So between Y and X, I have a 3.1. And then between Y and W, there's an H. This is going to give us enough information for us to set up a proportion of similarity. So if we go, we need to find the value of H. So I'm going to set up a proportion with H between our 2 triangles. Now H is in the same position as 5.5. So I'm going to go ahead and create a proportion for that and set it equal to another set of information. So what I have here is 2 numbers on the top triangle, 2 numbers on the triangle WYX. I don't want to use this value here because there's no value in that corresponding position. So what I want to do here is I want to use 6.3 and 3.1. Now, if we recall from chapter 8, we want to place the values in the correct positions. Because I took h from the bottom triangle and I placed it in the numerator, I'm also going to take the 3.1 from this triangle and put it in the numerator. They have to stay in the same places. So that means that our 6.3 goes on the denominator. And then we're just going to solve this by cross multiplying. 6.3 is equal to 17.05. Oops, 7. Let me back that up a little bit. I forgot the h. 6.3h is equal to 17.05. And then if we divide both sides by 6.3, change the color here, divide by 6.3, divide by 6.3, h is going to be equal to 2. Yeah, 2.7, and we're gonna round that up to a 1 because we're rounding to the hundredths place. So our height of our roof is 2.71 meters. The geometric mean of two positive numbers a and b is the positive number x that satisfies the equation a over x is equal to x over b. Now, in order to solve for x, if we cross multiply, we're going to get x squared is equal to a times b. Now, we could continue to solve this by taking the square root to both sides and getting x is equal to the square root of a times b. But we're going to go ahead and keep this equation here as our geometric mean because we're going to be applying that one to our geometric figures. All right, so let's go here. Let's use that one that I just showed you. X squared is equal to a times b. That's going to help us find the geometric mean of these two numbers. So what I'm going to do here is I'm going to do x squared. I'm going to replace a with 24 and b with 48. Okay, now what we're going to do here is going to be simple. We're just going to multiply 24 times 48. So these two get multiplied to give us 1,152. X squared is equal to x squared. So then we are going to take the square root to both sides to eliminate the exponent. Boom, boom. Okay, so then that's going to give us x is equal to 33.94. All right, and that would be the geometric mean of our numbers 24 and 48, 33.94. Your geometric mean should always land in between both of your values, so 24 and 48. If you get anything larger or smaller than 24 or 48, then that means that you did some calculation incorrect. All right, so let's go to the geometric mean theorems. So we're going to start with the geometric altitude theorem, which states that in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude is the geometric mean of the lengths of the two segments of the hypotenuse. Okay, so let's go ahead and write this out. According to this triangle here, we have CD squared is equal to AD times BD. All right, so what exactly are these pieces here? And we're going to go ahead and name it so that we can figure out how to solve for the geometric mean of the altitude. So CD in this triangle is exactly that. It is our altitude raised to the power of 2. AD represents this piece of the triangle. So we're going to call that our first segment of the hypotenuse. And then BD, this section here, is going to represent our second segment of the hypotenuse. All right, so that is the geometric mean altitude theorem. We're going to go ahead and apply that to this one of these triangles here. On this triangle on the left, this side x represents our altitude. Okay, so we can use this form that we set up on the slide 10 as our altitude. So we're going to do the altitude raised to the second power, x squared, is equal to, looks like we're going to use first segment of the hypotenuse. So let's go back here. We're going to call this 3 here a segment of the hypotenuse. So our first segment is 3. We're going to multiply that times our second segment of the hypotenuse. Our second segment is 6. So we're going to do 3 times 6. Okay, now here, same thing as we did on the geometric mean ones, we are going to multiply square root giving us x is equal to 4.24. 4.24. So our altitude of the triangle on the left is 4.24. Now this triangle on the right, okay, we're not looking for the altitude, so we can't use the same setup over here. We're actually looking for one of our legs of the right triangle. Okay, so we're going to go ahead and come back here, and we're going to use a different geometric mean theorem, and this one corresponds to the legs. So here what we're going to do is we are going to see what each piece of the formulas that I have down here for you, what they represent. So I'm going to color code CB squared AC squared is equal to DB times, let's do AD times, and then the last piece is AB and AB. All right, so one of the things that both of these triangles have in common is this AB. It's on both of them. So what does that represent? Okay, let's take a look over here. AB represents our hypotenuse. Okay, so as part of both formulas that we have here, we have the length of the hypotenuse. Okay, so that's going to be important for us to know. And then we have CB, which is this piece down here, which is a leg of the right triangle, and then AC on the second equation is the other leg. All right, so this piece of information is going to be the leg squared. Whatever the length of the leg is going to be squared there. And then lastly, we have DB and AD. Now, what could that be? So, DB is this, and AD is this, but they correspond to two different equations. So how do we know, or two different legs, I guess, two different legs, how do we know which segment to use? All right, so I'm going to call this a segment of the hypotenuse, right? Because in both AD and DB are a segment of the hypotenuse. But how do we know which segment to use according to which leg? So let's look at the first one, CB and DB. CB, DB, right? If we do AC, that one matches with AD. Okay, so if we noticed, those two, the segment and the leg, okay, were both adjacent to each other. Okay, so we want the segment of the hypotenuse that is adjacent to the leg that we are looking for. All right, so here we have our leg that we're looking for. So we have leg, we have a value for that leg now. So y squared is equal to, now let's go ahead and go back and see what we're multiplying. So we're taking our leg, equaling that to the segment of the hypotenuse that is adjacent to that leg. All right, let's come back here. We have two segments. We have the segment that measures 2 and the segment that measures 5. but the segment that measures 2 and the one that measures 5, which one is closer or adjacent to our leg y? Yes, that would be 2. So we're going to use 2. Now, to clarify just a bit, let's say the y wasn't there. Let's say y was here. So then instead of using 2 as our adjacent segment, we would use 5 because that's the one that's adjacent to y. But in this case, we have y that's on this left leg, so we're going to use 2. We're going to multiply 2 times, let's go back, so it looks like the hypotenuse. So this is where you want to be careful with some of these problems, because we don't want to multiply this times 5, because 5 is a segment of the hypotenuse, not the entire segment. So our entire segment is 2 and 5, which is 7. All right, so then let's do geometric mean for this. 2 times 7 is 14. Let's bring down our y squared. We're going to take the square root to both sides of 14, which is going to give us, let's see, 3.74. So y is equal to 3.74. So our leg here measures approximately 3.74 as we are rounding to the nearest hundredth. Well, that is the end of our Chapter 9, Section 3, Similar Right Triangles. I hope you learned a thing or two about finding similar right triangles, finding the geometric mean, and using the geometric mean to find the altitudes and or legs of a right triangles. If you have any questions, comments, or concerns, feel free to leave a comment in the tell section down below.